Okay, good morning. Today, what I'm going to do is try and move on a little bit ahead in terms of delivering this lecture. The reason is that we are missing out on a couple of lectures due to our topic exams. So this, I hope, will be able to guide us, help us through in covering our curriculum, and at the same time, we got more time in order to review some of the materials that we have. So I made some revisions on the slides that I put up on Moodle, so I'm going to do this fresh upload of the set of slides, but not so many changes. You will find basically in terms of the figures that I currently show here in this lecture. So let's begin. So this is chapter 7 of the text, and we are looking now at the atomic structure and periodicity. This takes us back to what we have covered early on. Early on, it was a very introductory statement to what an atom is like. And we looked at the development of this atomic theory, and a few names I'd just like to bring that on. First is a work done by Lavoisier. Lavoisier, as we looked at, used in the study of gases on determining actual quantities. In other words, the stoichiometric quantities when you're combining or reacting gas molecules. And essentially it gives rise to the stoichiometry, which we know in a chemical equation. Now, that work, set from the experimental evidence of the study of matter and changes, led to the proposal by Dalton. What did Dalton say? That the atomic model based on Dunlop, that the atom is the finest indivisible part of an element, and all the associated properties of a particular atom of the same kind, pretty much have the same properties or similar, same features, whereas atoms of different elements will be different. So with that in context, we are going to now be looking at the structure of atom in more detail. The question naturally, if the finest particle of matter is an atom, the question is, what is an atom? Or what does it look like? In our first slide, you see that the different colors that is produced in fireworks. Why that? That is because when we're going to study this topic, we essentially want to dwell on light and its properties. And that's where we're going to start. And so, let me begin on that. When do we get all these different colors in light? And why do different chemicals give us different colors? And some examples, we will show that as we go through the slides today. But we'll talk about that as we discuss light in general. Now, the name light basically is a subset of the whole term, which we refer to as electromagnetic radiation. Electromagnetic radiation covers the entire range of the different types of light. And we will use that, and we're going to look at the different components. Electromagnetic radiation is a form of energy, and that is light is a form of energy. And you can characterize light by these three parameters: the wavelength, frequency, and speed. Now, wavelength or the distance between two waves, and we use the positions or the locations, that is the crest of two waves or the troughs of two waves. And the second is frequency. Frequency is the number of waves passing at a particular time. So it's given in terms of per time unit, which is second. Now those Greek symbols I use, wavelength is lambda, and frequency is nu, which is the symbol for frequency. And the speed of light. The speed of light is a constant. And this constant is taken from the speed at, or when light passes through a vacuum. And you're looking at speed of light close to 3 times 10 to the power of 8 meters per second. That's quite a lot of speed. Now, just for comparison, for our sake, is that the speed of sound is about 340 meters per second, that sound. And a jumbo jet roughly is about 920 kilometers per hour. That comes to 255, so less than the speed of sound. So you see that light is a lot more faster than the other speeds that we are close to. Now, in terms of characterizing light or electromagnetic radiation, you see that wavelength. Wavelength is a distance between two crests. That's a wavelength. And you can see that this particular light energy, if you like, is essentially that specific wavelength. And if you can see the color from the slide, this is a red to indicate the sort of relative wavelengths of the different colors that we see in light. And this one, if you're taking the distance between this point to the, you have 1, 2, 3, and 4 cycles. You have 4 cycles of wave that is passing through. And that 4 cycles translates to 4 cycles per second, and that essentially hertz, the unit of frequency. Now, if you look at the green light has a lesser wavelength. Look at this wavelength, green. You have 8 cycles per second, that's 8 hertz. And you can see that essentially is where the green light, in terms of position, in terms of the difference between the red and the green. And here, right down below, you see the blue light. Blue light is a lot shorter in the wavelength, much shorter, but you can see that its frequency is a lot higher. So the two, frequency and wavelength, are inversely related. Now, the same concept you can relate to in terms of wave. Here is a normal ocean wave, and you can see the darker and the bright spots. Those essentially are the crest and troughs. The troughs are the darker portions of the wave, and the crest are the brighter. And that essentially is the same concept we're talking about. In light, you would also anticipate this sort of characteristics, and that's what we're referring to. But one thing that we will emphasize here, this is on a macro scale, large, where you're talking about wavelengths in terms of meters or kilometers. Here, when we're coming to light energy, we're really getting into the micro scale. Really, we'll give some dimensions as we continue. So here is the whole spectrum, electromagnetic radiation spectrum, and you will see that it begins, it starts from the lowest wavelength, which is the gamma rays, right up to the highest wavelength, the radio waves. And right in somewhere in the middle, we have the white light. The white light is the visible light, and that is what we normally operate in. That's where we have the rainbow color. From violet, blue, right up to red. I'd like you to note the relative positions of these colors. The blue light or violet light is 4 times 10 to the power minus 7. That's about 400 nanometers. This is in meter scale on the slide. 4 by 10 to the minus 7 meters. In nanometers, that would be 400 nanometers. 400 nanometers right up to 700 nanometers. 400 nanometers is the blue or violet end. That's the short wavelength. And then we have the long wavelength, which is the red. And that is about 700 nanometers. So you see the different ranges here. And one other point that I would like to emphasize on this visible white light, and that is the continuity of the radiation. So you see here a continuous band. That essentially arises from the diffraction. We're going to look into that, the diffraction of white light that gives rise to that rainbow color. Now, another form of light you will see is what is shown in here. Here you don't see the exact rainbow, but this is from a pickle, moist pickle, and essentially you will see that this is just of one type of color, and that is the orange color, which is basically due to the rich content of sodium element that is present within this. Sodium present in the salt, and that's what is coming out in the glow for the emission, the emitted spectrum for pickle. Now the question is, why don't you see the full spectrum of visible light in that? And that's what will lead us to discuss in the next series of slides. And that is, the energy of light was actually studied by someone by the name of Planck, Max Planck, a German scientist, and he came up with the relationship that relates energy. What was important in Max Planck's study was that he was able to establish some very unusual characteristics of light. And essentially his experiment was on the heated bodies, in other words, heated object at high temperature, and study the intensity of as a function of the wavelength of those different materials. And he essentially found that as you increase the wavelength, the intensity rises to a maximum and then drops to a low value. And that was something very unusual in observation compared to what is believed and understood at that time. And what is understood at that time, that the relationship between wavelength and intensity was that there is a continual increase in intensity as you approach the lower part of light wavelength. So the idea of just a maximum and dropping back to low was astounds these scientists, and they weren't able to really come up with an easy explanation at the start. But however, based on those results, he came up with the equation that relates energy to wavelength and likewise frequency. And that equation carries Planck's constant. So the equation is the energy can be equated to the constant multiplied by the frequency and hv. That's the energy of light from Max Planck. And what is also important is that it can be calculated as whole number in terms of the different multiples of whole number here in the energy. So essentially what concludes out of that study is that light comes in packets or particles. A system can transfer energy only in its discrete packages, and that is called quantum. And the word quantum, as we know now. So energy then seems to come up with another concept, and that is energy is not just a wave type of system, but is actually also is behaving as a particle. So, according to Max Planck, the energy is quantized, and the electromagnetic radiation particles, which is called photons. This is actually the term that was used by Einstein, photons. You can determine that energy of photons by that equation. Energy is equal to the Planck's constant multiplied by that frequency. Now, frequency is related to the wavelength, and that is basically the speed. That speed, which is c in that equation, that is the speed of light. And I've already given you that the speed of light in the Price light and wavelength. So this equation here relates pretty much the energy as a function of a wave. And the wave, you can characterize wave from wavelength and its speed or frequency. And the important term that we are looking at is Planck's constant, which is the value that came up in that equality sign. Now, what followed on from Planck's study is the work that really brings a huge revolution in this area, and that is the work done by Einstein regarding photoelectric effect. Essentially, what photoelectric effect is shining light onto a metal surface, and then that energy possessed by light, which is in photons, will be able to eject electrons out from the surface of the metal. And if this study is carried out in a vacuum, that essentially is what a photoelectric effect is. And one of the interesting features that came up from the photoelectric effect study, this is by Einstein, was, let me go to the next slide, this slide that is shown. You see here in the different colors, the green and the blue showing you the actual forms of the wavelength. Green wavelength is about 550 nanometers, and the blue wavelength is about 400 nanometers. Refer back to what I just highlighted in the earlier slide. And this is for a potassium metal surface. And what we are getting is that in the green wavelength, you see that when green wave hits the surface of metal, it was able to dislodge an electron. And that's the speed of the electron that is ejected from the surface of the metal. And once again, if you do that at 400 nanometers, which is the blue, you have the speed of electrons, and you can see that those are respective speeds which are not equal, or they are different because of the different wavelengths. And note what we also showed in there. For 550, it shows there 2.25 electron volts. Electron volts is the unit of energy. So we can convert that to joules. 2.25 electron volts, and this one is 3.1 electron volts. But I want to highlight what happens in the red. You see, red is about 700 nanometers. If your radiation is purely red, red light, when it's coming through onto the surface, nothing happens. So in other words, only certain frequencies or certain wavelengths can enable this removal of electron, or the dislodging of electrons from the surface of matter. So the idea of a threshold frequency comes in. So not all frequencies will be able to eject electrons from the surface. There is to be a minimum where you can then begin to remove electrons from the surface. And that was a very important findings. And from there, Einstein confirmed the particulate nature of light. And that is, light contains discrete packages, as from Max Planck, but he coined in the term as photons. Photons are discrete particles of light that contains matter-like property, meaning that it has a unique mass. So then came this famous equation, that is the Einstein's equation, that energy is equal to the mass multiplied by the velocity of light squared. So we have here this equation that relates light as particulates, which is a matter with a mass and its velocity. And also we have Max Planck's equation, if I go back, Max Planck's equation where you have light, which is a wave, and you relate that according to the equation described by Planck. So naturally, these two, if they both describe light, you should be able to then combine these two equations. But what is coming to light then, and that is, light has a dual nature. It has particulate properties, and also it has wave-like properties. Now that essentially is a new idea, or a new concept altogether, compared to the laws of classical physics at that time. So it wasn't just something that was easily embraced by the scientific community when this proposal came up. However, based on experimental evidence, they got a lot more confirmation, a lot more substance in this behavior. That's why they have to explain it in some new model. And that essentially is what is leading us to the atomic model. So, following on that, then came the equation that combines the two, the wave nature of light and the particulate form of light, and that is the equation by the French scientist Louis de Broglie, which essentially combines Einstein's equation and Max Planck's equation. And you can see here wavelength is a function of constant, and the mass of the particle, or you can see the mass of the particle, and then the velocity. So here we have pretty much now the equation that is going to be guiding the future part of the development of this atomic theory, the atomic model. Brogly's equation. So in other words, what de Broglie basically put together is the nature of light in terms of a particle and also as a wave. Now, let's just work on some of the aspects of what we know, or what affects about light, and that is, there are two kinds of spectrum we can observe. One is the continuous spectrum, and that continuous spectrum is when you split up the white light. When you pass white light through prism, you will see all the different bands of color. And that color from violet right up to red, that's continuous right through that range of wavelength from 400 to 700 nanometers. Now, another type of spectrum is when you have an element that is, let's say, heated at a high temperature, or an element that is emitting radiation. And when you have an element, what you will find is that this will give not a continuous spectrum, but essentially very defined spots or lines here. And we call that line spectrum, that basically it's discontinuous, and that line corresponds to the unique wavelengths of that particular element. Say, for example, for hydrogen, if you have a hydrogen source, so this light essentially is showing the white light diffracting using a glass prism, and you see all the different bands from red to violet. So it's, when you combine all these colors, you get the white light. But that's the hydrogen spectrum. If you look at the hydrogen spectrum, these are the four unique lines that occur in the visible. And you see that one line is at 410 nanometers, the other is a blue, which is 434, and green, 486. Then you have 656 in red. Now those four lines really comes from what is characterizing the nature of the hydrogen element. So why is that giving those four lines? And we're going to look at the structure of the hydrogen in order to explain that number of lines and the different colors in that. So what is significance about the hydrogen spectrum? What we can say that, like what Max Planck observed or proposed, that only certain energies are allowable for the electron in the atom of hydrogen. So that quantized nature is fitting pretty much in the line spectrum of the elements. The energy of electron in hydrogen is quantized. Okay, I'm going to skip this slide and move on. So that led to the first atomic model. The first atomic model, essentially by Niels Bohr. What Niels Bohr states is something quite unusual, because this is beyond what is currently believed and understood in terms of classical physics. And what he said is electron in hydrogen move around in the nucleus in certain allowable circular orbits. So if you consider the planetary system, where the sun is the center and all the planets revolving around the center, essentially that's the model very close to what Niels Bohr stated. That the Earth is moving in a circular orbit around the sun. In the same way, these electrons of the element hydrogen essentially is revolving around the nucleus in circular motion at fixed orbits. Now, using Niels Bohr's model, he applied it to hydrogen, and that really was a success. It fits perfectly with the hydrogen emission spectrum. So he was able to explain how those four different color or lines in the hydrogen spectrum very, very correctly, successfully. So it comes with this statement, and that is for the electrons in an atom normally rest in what we call the ground state. Now, when electrons are promoted to a higher state, the ground state is stated as the lowest, which is the beginning of the energy levels, and that is 1. And when they are promoted to, say, 2 or 3, this is what we call the quantized levels within the atom. So essentially, this is what Niels Bohr was postulating. Here is the electron energy level of a ground state, right at the first energy level. Now, in the second energy level, third, fourth, and fifth, these are states, but can be vacant. And we know that hydrogen only has one electron, so the single electron will basically be in the first energy level. That's the lowest, which is the ground state. Now, what these electrons can experience is that they can move up to second, third, fourth, or fifth energy level. And when they do, they won't remain in those levels for a long period of time. They will fall back to its usual state, which is the ground state. So that process essentially gives rise to what we call the emission spectrum. That's the color that we observe from each of these elements, because each element has a unique spectrum based on, one, the number of electrons that are here in the ground state, and also this gap or the energy levels. So what we are seeing in hydrogen, you can see here, hydrogen has the red, the green, and the blue, and you can see basically where those colors are coming from. The red, the green, and the blue are coming from the transitions that are taking place from, say, the higher energy level. Here's 5, the 5th energy level, going to the 2nd, and from the 4th going to the 2nd. So this too has different quantity of energy. That's different quantity of energy. And likewise, the red, that's a different quantity of energy. So these are the energy states that we see in the spectrum of hydrogen. So this is another representation. You can see here the red color that we see essentially is the falling from a high energy state to the second, and the green color, you can see it's from the high energy state, which is the third, to the second, and this one from the fifth, sorry, this is the fourth, that's the third, this is the fifth to the second. So that's the representation. So those line spectrum essentially are due to the transitions coming from the higher energy level to the lower energy level. So some of the things that I'd like to highlight regarding Bohr's model, those are the fixed circular orbits, and you can basically see the transition, you can take the transitions from a higher level to the lower level. Now the question you might ask, is what about the transition from this level to 1? For example, here, from 2 to 1. Yes, that does take place. But when that takes place, you can see that the amount of energy is a lot higher. In other words, that energy will not be able to occur or be visible or occur in the area of the visible. So we can see that small energy transitions, which occur in the visible, but the high energy transitions, that's not visible to the naked eye. And that is what we call the ultraviolet region. So if you have the energy from here, say for example, falling to 1, that is a high amount of energy, and you can see the difference in the gap. High amounts of energy, and that energy will be no longer be in the visible region, that will be in the ultraviolet region. So Niels Bohr's model can accurately determine the amount of energy between the transitions. In other words, the change in energy when you have an electron falling from a higher energy level, for example, the 5th energy level, to the 2nd energy level. So you can work out that quantity of energy, and this quantity of energy essentially is multiplied by a constant with the differences in the two levels. And you can see that this equation has the same form as Planck's equation. So the constant here is different because you will see that you're going to just simply apply the energy levels in this two. This is the final energy level squared, and this is the initial energy level squared. And note the negative sign. The negative sign will take care of the negative number when you are subtracting these two values. And this constant unit, it's in joules, and this is often referred to as the Rydberg constant. But essentially, this equation is the Niels Bohr's equation. So when you go back, okay, let's take the equation for Niels Bohr's atomic model. The transition energy, or the change in energy in the transition of electrons from where it was to where it falls to, where it was initially, is given by the equation. So notice here that this is the final level where it reaches or ends up with, and this is the initial. So using this, we should be able to calculate certain values of energy. For example, in here, the color of light emitted when an excited electron in a hydrogen atom falls from, let's look at this first one, from the 5th states, energy states, to the 2nd. And if we apply this in Niels Bohr's proposed model, you will see that this is essentially the equation setup. So change in energy is a constant with one of the final squared and one of the initial state squared. So you put it in the final to be the 2nd, and the initial be the 5th, and then you take that, you multiply that to the constant. That will give you the value of the energy. Now the energy units is in joules, and that energy is the same because of the relationship to the wavelength based on Planck's equation. Planck's constant multiplied by the velocity. This is the velocity of light divided by the wavelength. So if we try to work out the wavelength of this transition, we can make that wavelength the subject of the equation, and we can now obtain the wavelengths. Since we have the energy term, and these two are known. So if we make those substitutions, we'll come to the value as shown in that answer. So in the first transition, the 5 to 2 was 434, which is the blue light. This is where the blue light occurs in the electromagnetic spectrum. In the 4 to 2, that's green, which is 486. And 3 to 2, this is the orange or red, that occurs at 657 nanometers. In other words, that's basically how those line spectrum of hydrogen is demonstrated based on the transition of electrons. So in other words, we are looking at the elemental spectrum, which is based on the emission properties of the electrons within the element. So hydrogen is a very simple element. There's only one single electron. So this description really fits perfectly into what Niels Bohr stated. So let's just summarize Niels Bohr's model. The model correctly fits the quantized levels of the hydrogen atom and postulates only certain allowable circular orbits for the electron. So one thing about the circular orbits was found to be correct, and those were quantized levels. And as electrons becomes more tightly bound, its energy becomes more negative relative to the zero energy, that is the reference state of free electrons. As electrons is brought closer to the nucleus, the energy is released from the system. So you can see that essentially is the negative value that we see in that quantity of energy. So Niels Bohr's model is correct for the hydrogen, but when you take elements other than hydrogen, that was when it begins to began to can we start? So the Niels Bohr's model fits correctly with the quantized nature of the energy levels of hydrogen, and that fits perfectly. Now, one other observation: as electrons become more tightly bound, its energy becomes more negative relative to the zero energy. And as electrons is brought closer to the nucleus, energy is released from the system. And that, I've already highlighted that in terms of the sign, you can see that the energy is actually a negative value. And as electrons are closer to the nucleus, you have a lot more energy that is released from the system. So Bohr's model was able to fit for hydrogen. However, when you try elements other than hydrogen, that's when the model began to fail. So this model only works for hydrogen. Electrons move around the nucleus in circular orbits was fine, or it was correct in terms of the description of hydrogen, but when it comes to the other elements, that's when it began to falter. Okay, so let me move on to the next component in the atomic model. What we have was the equation that was derived by de Broglie, and basically bring the two equations together, Planck's equation and also Einstein's equation. One on the wave nature of light and the other is particulate nature of light. So when you combine those two, de Broglie brought in the relationship relating wavelength to a constant, which is Planck's constant, and the mass and velocity. Now, if you rearrange that equation, this equation, this is, let's say that's the wavelength, and this is the mass and velocity. Mass and velocity, if you know, that is basically the momentum of an object, or a particle in this case. And this is the change in x, which is essentially the change in the wavelength. Now, when we're looking at this change, we're essentially looking at the possible ranges or the uncertainty. And that's where we are coming to. In other words, predicting the position of an electron at any point of time is really impossible. And it's only coming from this equation, which is known as the uncertainty principle. Uncertainty principle is proposed by Heisenberg, and using the de Broglie's equation and using the error from that particular relationship, was able to work out the error, the proportion of error or percentages of error in that relationship. And that essentially is what gives rise to the uncertainty principle. And that's the uncertainty in the momentum, and that is uncertainty in the position. Planck's constant. And you can see that these two values, these two parameters essentially is related to a value greater than or equal to a constant. That's Planck's constant with a pi term. So what that means is what we now know as the wave function. And the wave function symbolizes by that symbol. The wave function indicates the probability of finding an electron in a position or point within an atom. And that gives rise to this concept, and that is the probability distribution. So the wave function is essentially the probability distribution of electrons in the atom. And if you're looking at how that relates to the how electron is positioned within an atom, that essentially is the S wave function. That is the spherical shape wave function. That's the probability of finding an electron. So wherever you see a much darker region within that diagram, that's when the highest probability of finding an electron. And as you go that, you can see that it becomes more lighter towards the peripheral of that, meaning that there's a lower probability of finding an electron. So if you're looking at the probability of finding the electron, so for the wave function S, closer to the nucleus, if this is the distance from the nucleus and this is the position of the nucleus, closer to the nucleus, you'll find a lot more concentration of electrons, a higher probability. But as you move out from the nucleus, that drops in terms of them. That is for the S wave function. And notice that this we are representing as a wave function. The first being the first energy level, and S is the shape that is generated by that particular probability wave function. Now this is two views of representing this. This is sort of the plan view from the top. You can see here that essentially is the probability of finding the electrons within around the nucleus, and you can see that closer to the nucleus you see the more concentrated form of the color or intensity of the color, and that essentially is where you have higher probability. And that is a much more another way of representing this on a side view, looking at the radial probability. So if you like, this is where electrons, the highest probability of finding electrons at that particular level, which is at a certain distance from the nucleus. So here we are talking about the S probability distribution. Now, in terms of the probability distribution, you will see that the relative orbital size is difficult to define precisely, and the orbital is the term that we're going to use to describe the wave function, which is the probability function. So this is the term that we're going to be using. So when we're referring to orbital, that essentially is the probability distribution of the electrons. The picture of an orbital as a three-dimensional electron density map. So this one, instead of what Milbohr actually stated, that it is a circular orbit, this one gives you a much more complete picture, which is a three-dimensional representation. So instead of a circular orbit, for example, in the S orbital, is actually a spherical orbit. So hydrogen is a 1s orbital, the radius of a sphere that encloses 90% of the total electron probability. So that intense or darker region represents a 90% of probability chance of finding the electron in that particular region. And that's related to that region that we are looking at, where the maximum is. So what essentially gives rise to or comes out of the wave function are essentially the various parameters that defines the position of the electron. One is the principal level, and that is known as the principal quantum number with a symbol n. So here it represents the size and the energy of the orbital. And the other is the angular momentum quantum number, and that relates to the shape of the orbital. And we're going to look at the shape, essentially the subshells within the principal level. And then you have the magnetic quantum number, which relates to the orientation in space of those orbitals. So these three are going to be the first places, which are basically the solutions to that wave function that that comes up from the Heisenberg's and de Broglie's equation. So this is basically the summary of how the electrons can be described in an atom. And that is, if you have an electron in the first energy level, that's the principal quantum number, and you have the secondary quantum number, that's principal, the secondary quantum number, and then you have the magnetic quantum number. Those are the three sets of quantum numbers, or three sets of the wave function solutions that we will start off with. Notice that for the principal principal quantum number n, the value of L is 0, and that represents the s orbital. So in other words, L is specific to the shape of the orbital. So for L to be 0, the shape is S. And in the S orbital, spherical, the orientation in space is only 1. So you have this orientation to be 0. And number of orbitals is 1. Now if you go on to 2, that is the second principal level. Now the possible values of L in this one, you will see that is 0 and 1. So in other words, from the principal quantum number, the possible values are 1 less than the principal value. 0 and 1. For the 0, you have, that's the s orbital. And in the s orbital, there is no orientation, only 1. So here you have number of orbitals 1. But when you look at the L value of 1, this represents the second type of orbital, and that is the p orbital. Now, if this is spherical, this is going to be slightly different in terms of this path. So the probability path of this, you'll find in the diagram coming, is different. And the orientation really takes a 3. So it's no longer spherical. It is going to be something that you have to describe it in the 3 different coordinates. The x, y, and the z. So you see these numbers here coming because of the 3 different orientations. So the number of orbitals here for the p is 3. So in the second energy level, you have 3 p orbitals and 1 s orbital. In total 4. Now we go to the third. Now we introduce the third orbital. This is s, and that is p. This is going to be d. Now in the d orbital, you can see the orientations are a lot more complex. There are 1, 2, 3, 4, 5 different orientations. So we're going to be looking at the basic x and y axis and z. Now we're even going to include 2 more in there. And that was part of the solutions to the waveform of the d orbital. And then you come to the f orbital in the fourth. You can see that in the f orbital, you have 7 different orientations. 7 different orientations. So you can see that the number of orbitals increases as you increase the principal quantum number. Those have very specific, and these are the different levels or sub-levels. These are the different sub-levels that are present within a level itself. So for example, in the 4th level, you have 1, 2, 3, 4 sub-levels. And here you have 3 sub-levels and 2 sub-levels. Here there's only 1. So let's look at this. For principal quantum number n is equal to 3, determine the number of allowable sub-levels. That is the different values of L and give the designation of each. So let me take us through with that. So if n is equal to 3, best way to represent this is to write up the 3 different consecutive sublevels based on the principal level. So this is the principal quantum number, that is the secondary quantum number, and the magnetic quantum number. So if you have 3, what are the possible values of L? 0, 1, and 2. Note the way that I've represented those following a column, because I'm going to take each one of these sublevels. So for the essentially when you are writing out the possible values of L, it'll be from 0 to n minus 1. That's the general rule of filling up the secondary quantum number, or L. So in this particular case, we can then consider the magnetic quantum numbers. If you have 0, there's only one orientation, and that is just 0. Here, if you have minus 1, there are 3 different orientations. Minus 1, 0, plus 1. And for the 2, you start from minus 2, minus 1, 0, plus 1, plus 2. So in terms of number of orbitals here, there will be 3 orbitals. Here is only 1 orbital. And out here is 5. And what are these designations here? For L value to be 0, we know this is the s orbital. So in the s orbital, which is shaped spherical, there's only one orientation. So there's no orientation indicated or shown in there. So in the p orbital, you have 3 different orientations. And the 3 we can simply use the x, y, and z. And that one is the d orbital. D orbital, you will see that it has 5 different orientations. And those orientations, I'm going to show that on the slide, what they are. Okay. Let's go on to the different orbitals. So that's the s orbital. The s orbital essentially is a spherical, so there's only one single orientation because you don't have any changes if you're looking at it in x, y, or z axis. And that's the s orbital representation. You can see that for the s for the principal level 1 is smaller in size compared to the s in principal level 2, whereas s in the principal level 3. So here you can see that the increase in the principal level, the size of the orbital also increases. So that's 1s, 2s, 3s. P, this is the shape of the p orbital. You will see that the p orbital essentially is a double lobe, and the double lobe can be oriented in the x, y, and z. So it's x direction, y direction, and z direction. So this will be px, that will be py, that will be pz. Now you can see that out of those, you basically will be able to tell the boundary. This boundary lines is where the nodal points. In other words, that's when the waves cancels out, and you don't have any probability, or it's almost 0 probability of finding electrons at those points. That's what we call the nodal points. Now the D orbital, you have 5. So you can see that D, Y, Z orientation is this one. This is D, Z squared orientation. This is DXY orientation, DYZ orientation, and then DXY x squared, y squared orientation. So those were the 5 different orientations. So it's a little bit more complex than the p orbital. So those are the d orbital shown. It's xz, yz, xy, and then x squared, y squared, and then dz squared. Now the red F orbital, there are 7 different orientations, and all these are the different 7s. And you can see that it's a lot more complex because you are dealing with a lot more integrated number of orbitals that are within each of those orientations. Now, before we go on to actually fully describe the behavior of electron in this orbital, we'll bring in the last set of solution to the constant number, and that is essentially the Pauli spin, that is the electron spin. That is, in any orbital, you'll have a maximum of 2 electrons, and those 2 electrons will spin in the opposite directions, the plus and the minus. We call that the Pauli exclusive principle, and Pauli states that in any given atom, no 2 electrons can have the same set of 4 quantum numbers. So in other words, in each orbital, you have 2 electrons, and those 2 electrons have got basically unique sets of quantum numbers. No 2 electrons will have the same. And an orbital can hold only 2 electrons, and they must have opposite spins. All right, so what I want to do is give you an example of what we are discussing, just to finish off this part of the lecture. And this is what I want to get at. So now when we apply this quantum model to atoms, this essentially is how we're going to represent them. So within each atom, you'll have electrons. And these electrons, we can assign its different sets of orbitals based on this atomic model. So we have here, and that essentially is what we call the Aufbau principle, which is the electron configuration or the electron structure. We have here an example like oxygen. But before we go into oxygen, I will take you with a hydrogen. Hydrogen is 1 electron. So that 1 electron will be in the ground state. So the ground state of hydrogen is in the first energy level. And what is the orbital that is in the first energy level? It would be the s orbital. And how many electrons can fit into that? 1 orbital can take 2, but since hydrogen only contains 1 electron, that's the 1 electron. So this is electron, this is the orbital, and this is the energy level. So let's consider oxygen, which is given in here. Oxygen is 8 electrons. That's atomic number 8. 8 electrons. So you can see that in the 8 electrons, 2 occupy first principal level, and 6 occupy the second principal level. Second principal level you can tell from the 2 numbers. The 2 that is present in there. That's 2 and 2. That's in the second principal level. Now, in terms of the filling up of electrons in these orbitals, we follow what we call Hund's rule. Hund's rule essentially that you start from the lowest and you work up, and also when you're filling up any orbital which is degenerate, meaning on the same level, you have to start with the same spin. Let's illustrate that with oxygen. That is shown in here. So if we write, let me show that on the board. If we write electron configuration, of oxygen, atomic number 8. So that means it has 8 electrons. So if you write the electronic, let's just do the N, L, ML, not only bring in the last MS. So the first level, this is 0, magnetic is 0. How many electrons? One will be spinning in the positive direction and the other in the negative direction. So we represent each electron as a half. That's the value we assign the electrons. So this should be nice. So this is the 2 electrons, which is 1s2. And you go into the next 2. What are the possible values? 0 and 1. And now, for this, the possible value is 0. And how many electrons can fill up this? Also 2. 1 positive spin, 1 negative spin. So now this is 2, because it's an S, 2s2. Let's go on to the next one, that's P. What are the possible values? -1, 0, +1 for oxygen. So 2, 1, -1. This is where we're going to bring in Hund's rule. How do you fill up this? We're going to start with positive half, another positive half, another positive half. How many electrons do we have there? That's 3 in the p orbital. What's the maximum? It can be 6 altogether maximum. However, you only have 4 more. There is 2, 4. You need only 4 more. If there is 3, the next 4th one, you start from there. That's how we fill up using Hund's rule. When it's degenerate orbital, meaning the same energy, same orbital, you start with the same spin, and then you pair up. So this is going to be 2p4. 2, 3, 4. So you can see here very clearly the one that is paired and the 2 that is unpaired. And this are both paired up. And this is the off-Bohr diagram, and this is actually the quantum numbers or quantum solutions of the oxygen atom. So we can represent this in a box diagram, and that box diagram I want to show, and that is on the slide. So if you look at the slide, the box diagram, this is 1s2, that's 2s2, and this is 2p4. And the box diagram essentially shows the paired 2 electrons of opposite spin, 2 electrons opposite spin in the second energy level with the s orbital. Here, second energy level with the p orbital. 1 already paired, 2 are unpaired. two orbitals represent what we call the valence. Valence is the outermost or the highest energy level. So how many electrons are there in the valence principal level, or we call it valence shell? 2 and 4, altogether is 6. So in other words, the valence electrons of oxygen is 6. The inner, or what core electrons, is 2. So that's valence electrons. Valence electrons are the outermost, the electrons in the outermost principal quantum level. So here we will see the periodicity within the periodic table. For that, I'm going to bring it on in the lecture, as a second lecture. So we will finish off this lecture right here on this slide on valence electrons and core electrons. Thank you.